Let me see if I can share my screen. So, right, click on share. Can you tell me whether you can see that?
Yes, we can see the screen very well.
Okay. So let's turn that into presentation mode.
Okay.
Still working?
Perfect, yes.
Excellent. Okay, so the only thing left is to change this to a laser pointer. Right. So good afternoon, everyone. Thanks, William, for the introductions. Now, I'm going to admit that when Corinne invited me, I didn't know what to talk about. I've got no training in diversity agenda, and in a way, it's difficult for me because unlike some other people, my career path has been fairly straightforward. I did my undergrad in Australia. I did my PhD in Oxford. I did a few postdocs. Then I started my academic career. And even before I started my undergrad, I already know that I wanted to be an academic. And I was one of the lucky few who actually got my dream job. And now the fact that it's not at all like what I dreamed it is a different story. But I think I've been very lucky in the way that things worked out. So I thought about this, and I thought about what advice, what can I draw from my experience to actually give you the audience in terms of how the career path works out for an academics. And I thought it's probably easiest for me to fall back to my research. And I talk about my research, but I will slip in some comments on things that I think haven't been mentioned today, which is actually the choice of the research areas is one of the things that we tend to agonize over when we are at the beginning of academic career, or we're hunting for an academic positions. And that choice is a very tricky decision. And so I talk about the reasoning behind my choice of areas of research a little bit. Okay, so let's crack on with the main business. Now, this is an event, the Catalysis Hub. So we talk about catalysis. Now, generally, we divide catalysis into three areas. Heterogeneous catalysis is, we talk about bulk specialty chemicals. Homogeneous catalysis, very much about fine chemicals, organic synthesis, pharmaceutical targets, and that sort of thing. And then we have the sort of emerging biocatalysis area, where you got a lot of enzymatic processes that can do things that normally would take several steps in this sort of more traditional chemical pathway. So we're really talking about much more sustainable processes using much more, much greener reagent, much greener solvents, and you can still deliver very, very complex, high quality products at the end of these processes. And these are roughly the main areas in catalysis. Now, what I'm going to talk today is I'm going to focus on other things. So things that define these traditional classifications. So we'll talk about something about immobilized catalysts, somewhere between heterogeneous and homogeneous catalysis. And we move on to organocatalysis. And finally, we move to things, to the type of catalysis that doesn't pin down at a single molecule anymore. So catalysis at the interface, not heterogeneous, traditional heterogeneous. So we start with immobilized catalysts. So the story here is like this. Immobilized catalysis happens a lot. What tends to happen is that someone somewhere invented a new organometallic catalyst. It seems to work well, but they want to immobilize it to a solid so they can recover the catalyst and reuse it afterward. So that saves the cost, that makes the whole thing a lot more sustainable. What often happens in that process is that once you immobilize the catalyst, suddenly after a few cycles, the reaction doesn't work as well anymore. And the reason most of the time is because your metal centers and dissociate from the ligand, which is bound to the solid, and then they go into a solution, and that process called leaching. And once you got leaching going on, your catalyst died extremely quickly, you lost your catalyst, and so you can only recycle it a few times. And this happens very, very often in most cases. So it's not trivial to immobilize a catalyst. Now, when I came to Leeds to interview for the job, they were looking for someone in particular who is a physical organic chemist. So I'm really lucky there because they actually, the job description matched my research profile almost perfectly. So what they really want is someone who can figure out what's going on in the reactions and figure out a way to fix them, which more or less fall back to the sort of mechanistic approach to understand the process. So when I came to Leeds, one of the first process that I was shown that was being developed in Leeds was this immobilized catalyst here. So it's a very simple iridium catalyst based on a dimer with 2 chloride, H iridium, and a CP star, and you immobilize it to something called Wang resin, and then you got an immobilized catalyst. Now, the difference between this immobilized catalyst and other immobilized catalysts is that it can run up to 26 cycles with a small decrease in activity, not huge. But you can see up to, let's say, the purple line, 15 cycle, it's still almost as active as the starting point. So the other thing is that it doesn't leach. After 26 cycles, it only lost 3% of the iridium. So it didn't lose the iridium. Whatever deactivation happened is something else. So that's good, because the last thing we want is losing iridium, and there's not much to play with. If the iridium is still there, if we can figure out what's wrong with it, then we can get the reaction going. So the catalyst is for this transfer hydrogenation reductions in organic chemistry. It's nice in a way that you don't have to have special equipment for hydrogens. And so it's a very convenient way of reducing ketones and other type of compounds. So the reaction itself is not that important to us. The key problem with almost all the immobilized catalysts is like this. Once you immobilize catalyst, you can't characterize what's going on anymore unless you got the phosphorus ligand in there, and you can use solid state phosphorus NMR, which is still very tricky. But if you don't have phosphorus, as we do in this case, then there's almost nothing you can do to figure out what's going on other than monitoring where's your iridium. The iridium's there, and that's it. We can't figure out what's happening anymore. Now, the last bit of information I was given is that the reactivations can be done with HCl. You can wash the spent catalyst after 26 cycles with HCls, and then reactivate to get the activity back, but it only lasts for 3 cycles, and then it's dead again. So all this was published by my colleagues back in 2013. And when I came in, I understood why they brought me there. So I said, this is one of the priority projects that I want to tackle. So how do we go about dealing with this? Now, many of you are associated with the Catalysis Hub, so I'm not going to explain what XAS is. It's an X-ray absorption spectroscopy. It allowed you to get the information about what's around your metal center most of the time. So it works really well in solid state. In solution state, it works, but the data quality is less good. And so any scatter beyond 2.5 angstrom is difficult. So you can only get the sort of initial shell around the metal. Beyond that, it's tricky. The structural changes can be a little bit difficult to discern if there's no significant change in bond length or coordination number. Fair enough, because the data quality is pretty low. Now, if you talk about beam life scientists, then they will start talking about improving the sample environment, how to do data processing, and so on and so on. And I'm going to admit, I'm an organic chemist by background. I don't understand all those bits all that well. I can't really do that. But as a chemist, as an organic chemist, I start paying attention to all the other elements, things which are not metal. So this is the diagram for the absorption energies for most common elements. So you got all the heavy metals up here. You got the sort of base metals in the mid-range there. But all the soft elements are down here, lower energy. So if we can get the information, the XAS information for those elements, in addition to the information for the heavy metals, we actually got a much better pictures of what's going around the metal center. There's only one technical problem. At the palladium KH, which is 23 keV, you can go through 0.1 millimeters of PTFE like it's nothing. But if you move to the edge for potassium, sulfur, chlorine, and phosphorus, 0.1 millimeters of PTFE probably kill off all of your lights. So you got nothing coming through. So a lot more effort is needed to be spent on cell designs, materials. We had to work with fluorescence measurements, and you need to get a beam line. You need to find a beam line that's willing to let you change the edge just at these extreme ends. And so I was very lucky that I was in conversations with a few beamline scientists at the Grenoble synchrotron, and they wanted to try this out. They were actually looking for chemists to give them an example of a case study which would demonstrate what they can do. And so this is really a match made in heaven. And one of the key things that for anyone who's aspiring to be in academics is that when you start out, your money, your funding is tiny. And you really have to be very careful about anything you spend. The nicest thing with working with synchrotron people is that actually, if you put in a proposal and they give you the beam time, unless it's the American beam lines, the European one would basically pay for a lot of the thing, including flight tickets. So it really helps me at the beginning when I didn't have a huge amount of funding to get this sort of thing going. Anyway, so back to chemistry. This is the iridium XAS data. This is in R space. You can see the iridium carbon scattering there and the iridium chloride scattering band there. So the fresh catalyst got a lot of iridium chloride at the 3 cycles, still very active. It lost a significant amount of chloride. And by the end, it lost all of your chlorides. Fair enough. So losing chloride is bad news, but losing just one of the chlorides isn't a problem. The problem is when you treat the spent catalyst with HCl, so you reactivate the catalyst, it doesn't put back the chloride. It's not there. So the recycled catalyst, the red one, doesn't put the chloride back in. You still have no chloride next to the iridium. So that's one small win for us. We start to have an idea of what's going on. It's more the acid that's doing the job, not the chloride. But we still can't tell what are the structural changes with just the iridium data. So what we did is we measure the chlorine Zen data. You can't do exactly at this energy. You have to rely on Zen. Now this signal intensity tell us how much chlorine is in there. So at the beginning, you got lots of chlorine. After 3 uses, you start losing about half of the chlorine. And then by 26 cycles, you got very little chlorine left. Fair enough, that's consistent with the iridium data. But the most interesting one is when you treat the spent catalyst with HCls, you get this purple line. Now, first of all, there's some chloride there. But more importantly, that looks nothing like what we got to begin with. So the pre-edge is there, but all of these bits are new. That's a new chloride species in there. And so we started looking into what it could possibly be. We came up with various options. We started digging the literatures, and then we got lucky. In this literature plot of chlorine Zen, the KCl one looks suspiciously like the one we got. And so we took KCLs, we run the chlorine H Zen spectra, and which is the black dotted line, and it matches pretty much perfectly. You have to allow for the low quality of the data at this low energy. If you take away the pre-edge, which we know came from the catalyst left over, then everything seemed to match up. So we know now that we're making KCLs with the HCLs treatment. So now we got a theory. What we did is that we created the flow experiment and we put the catalyst into these cells. We do the fluorescence measurement here while we're flowing the reaction mixture through it. Now remember, you got the potassium terbutoxide here, and that explained the potassium chloride formation in the end. So as we do that, we can monitor the chlorine content, which is a blue square going down. So that's the chlorine H jump that represents how much chlorine's in there. We keep losing the chlorine or the chloride, but on the other hand, at the same time, we keep gaining potassium. Just more and more potassiums build up in the catalyst. And if you monitor the activity of the catalyst by analyzing the output of the flow reactor, it is decreasing in activity as you lose chloride and you increase the amount of potassium. So we arrive at finally at the full picture of what's happening in there by combining the data from the soft and the hard SACS data. So you start with something that looks like this as a pre-catalyst. You got 2 chloride on the iridium. When you start treating with potassium terbutoxide, you're going to lose 1 chloride, but now you got the catalyst. So 1 chloride still required. As time progresses, you still got the alkoxide floating about. So eventually that last chloride is gone. Now you got the deactivated catalyst, but the iridium got 3 alkoxides around it and the CP star. So it's now minus, and you need a potassium counterand. That explains the increase in the potassium content. Finally, when you treat it with HCLs for the reactivations, all that we did is to protonate all the alkoxide. We didn't put the chloride back in. So we now got the protonated alkoxide, which are a lot more lay-by, so you get more activity. But sooner or later, we're going to lose all these proton under basic conditions, and we're back where we are with the deactivated catalyst. So I can't tell you how we came up with a solution for all this. It is commercial informations. But based on this, the companies that commercialize these catalysts did, in the end, arrive at the solutions on how to prevent this process from happening and actually make it a much more reliable catalyst for the industrial partners. All right, so that's one example. Now I'm going to move on to organocatalysis. And the type of organocatalysis that I want to talk about is quite different from the type of organocatalysis that you normally would hear about, because this one is about carbon dioxide. So this is another thing I want to mention. This is actually the first grant that I've got as an independent academic. And at the time, I was aware of a very, very large drive for research into carbon dioxide capture and utilization. And so I took a very organic approach to it. And we wanted to look at conversion of carbon dioxide into useful organic compound with organocatalysts. And this is how we started these projects. So long story short, this is a known reactions. You got various type of catalysts. You got carbene precursor, phosphazane, but most importantly, most interestingly, you got this rather benign guanidine catalyst that can do the job as well. And that's quite interesting because how would guanidine activate the carbon dioxide to get the reaction going? So the group that found this catalyst proposed, based on some crystal structure of these very fancy crystal structure that they isolated, that the guanidine acted as a super base to deprotonate the amine to make it a nucleophile, and also to stabilize these carbamate counter anion by hydrogen bonding, because that's the crystal they found, which is not a bad hypothesis. So when we came into this, we asked ourselves the more important question, which is, why do we need this catalyst? This is a very expensive and unstable catalyst. Now, if the catalyst is acting as a super base and a hydrogen bond donor to stabilize the carbamate, then we can replace it with two catalysts. One is a super base, and the other one is a hydrogen bond donor that stabilizes the carbamate. So these thioureas are notoriously good at hydrogen bonding to things like the carboxylate or carbamate. So we did that. We replaced that expensive catalyst with two very cheap partners here, and we get the same yields. But more importantly, we did the control experiment. So we removed the thiourea, just the guanidine, and we actually got a faster reaction, which is a red one there in this kinetic plot, which is a very poor quality kinetic plot. But nevertheless, that's what we got at the time. Actually, the blue one, in the presence of thiourea, is slower. And so stabilization of carbamate anion here actually slow down the reaction. You don't want it stabilized. You want it to proceed to the next step in the catalytic cycle. So that a little bit of a flip of the concept from the original proposal. What we also done is we characterize the product properly, and it turns out that there's a second product. It's not huge amount, but at 60 degrees, you end up with about 15%. At 0 degree, you got nothing, but at room temperatures, you got about 3 to 5% most of the time. We were curious about these two products, so we spent about a year studying the mechanism of these reactions. I'm not going to go into details. We use every single technique we can find: IR, mass spec, proton NMR, silicon NMR, ZC for kinetic profiling. And in the end, we arrived at this type of mechanism. You got two pathways. At room temperatures, is the reaction between the amine and the carbon dioxide that is fast. So you end up with a sort of silide carbamate that then would undergo the reductions to give you the formamide as a product. However, at 60 degrees, suddenly the carbon dioxide can react directly with the silane and give you these formate, silide formate, which can also be further reduced to give you this acetal species here, and then that would give you the diamine species, which then would disproportionate to give you one molecule of the amine and one molecule of the formamide. So these are all in my publication here. But the real important discovery is not these. These are all very interesting academically. in terms of how carbon dioxide react with all this. But the real discovery is this one here. So this is at 60 degrees. 1 more percent of catalyst give you the red kinetic curve, and 5 more percent give you the blue. Now, we're only plotting the yields for the formamide, so that's why we don't get 100%. But if you look at it, the 1 more percent goes just fine up until about 10, 15 minutes, and suddenly it's just flattening out. That's the reason why the 5 more percent perform better. And so that's clearly a case where 1 more percent of catalyst just died off mostly at that stage. And so we need to look into catalyst deactivations. Now, once we know the catalyst die off, then the rest is fairly straightforward. We can react the catalyst with carbon dioxide and acetylene, and we find that it does form this kind of deactivated species. So just put the formamide straight onto the nitrogen there on the catalyst. The catalyst is actually a pretty good nucleophile, so that's unsurprising. We can characterize this with mass spec, proton, carbon NMR, and all that sort of thing. Now that we know how the catalyst die, it's easy to stop it. So all we have to do is to put another substituent on a nitrogen. Now we lock it up and prevent it from forming this type of deactivation product. So that's what we did. And then we found out that both of our new catalysts goes a lot faster than the original catalyst. Again, this is a plot just for the formamide. That's why the yields wasn't 100%. So the new catalysts are a lot faster because they are a lot more nucleophilic. We just put an electron donating group on the catalyst, making a lot better as a super base. But obviously, we can take it down to 1 more percent, no problem. Catalyst doesn't die. It takes longer. So at 5 more percent, the reaction's over in pretty much 100 minutes, and the majority of it would happen in the first 30 minutes. At 1 more percent, you need about 300 minutes to get the reaction completely finished. You got really, really high yields in all of these cases. At room temperature, you don't even see the amine, you just get the formamide. So far, so good. Then we went and say, well, we see how it works with 0.1 more percent. We're really pushing it here because normally you don't do organocatalysis with 0.1 more percent. That's really low. And it still works. Now, you can see the kinetic curve change. I'm not going to go into that discussions here. We don't have time. But we ended up with still 82% yield for the formamide after 24 hours. And we get really impressive turnover number and turnover frequency for this type of catalyst. So just to give you an idea, the original reported process in that paper give you a turnover number of 17 and a turnover frequency of 11.3 per hour. After all of our studies and improvement, we now got a turnover number of 820 and a turnover frequency of 34.2. So at the time when we published this is still the highest turnover number frequency and turnover number for this type of catalysis. Right, so I've gone fairly quickly through 2 topics. We got about 17 minutes left, which is probably not enough to go over the last one properly. But the last one is the one that really interests me because you can see the first one is the topic was actually chosen for me. I came to it, these are the problems people have that I need to solve. The second one was basically that was an area that was popular with the funder. I see how I can contribute to the subject. The third one is really something that we came up ourselves. We really love it, and we wanted to do it properly. So my interest here is in on-water reactions. Now, this is a term that refers to reactions where the reactants are not soluble in water. So what you end up with are emulsion of organics in water, and you get a lot of rate acceleration. This is a report in 1980 by Breslow, and he was studying the Darzander reaction. He found that actually, if he doesn't use methanol, he throw this organic partner into water, he get about 6 times accelerations of the reaction rate. And then if you throw it into lithium chloride at 5 molar, then you get 143 times accelerations. So the key thing here, from the point of view of sustainable chemistry, is that actually these processes are a lot cleaner, a lot greener, because you don't use organic solvents. And the workup is really trivial. So I'll show you an example of the workup. This is our gateway reaction to get into this area. We discovered this really by accident. So one of my students was making these salts here. So basically reacting the aminopyridine with the propyl bromide to get to this salt. So you got the ammonium cation, the bromium anions. And then you just throw that into sodium hydroxide solutions. Now, as soon as you throw the solid into solution, it reacts. It really is a very fast reaction. And by the end of the addition, you get two layers, the aqueous layer and the organic layer. And if you take the aqueous layer out, the organic layer is solidified into 99% yields of this pharmacore here. So amazing reaction in terms of green metrics. You don't even need to use organic solvents. Your workup is more or less just separate out the two phases. So we started digging into this area, and it turns out that the term on water is an umbrella term, and a lot of the reactions do not conform to the traditional definitions. Now, traditional definition is that both the organic reactants is in the organic phase, nothing in the aqueous phase. Most of the time, you got partial solubility, or in some cases, you got one partner in the aqueous phase, one partner in the organic phase, or most commonly, I think, you got situations where one partner needs to be activated at the interface and then it reacts with the other partners. And there are some theories on the background of this. Most of the time, people suggest that you probably had some sort of hydrogen bonding stabilizing the transition state. And in those cases, you get rate acceleration. See, rate acceleration is what we really want. That example I show you took 2 minutes. The traditional pathway takes about 48 hours to get to that particular pharmacore. So this is our reaction. We picked this one because we thought it's simple. It turns out it's the most complex case. So this is a simple Henry reaction. You got this nitromethane adding to that ketone, the activated ketone. You end up with this product. Straightforward, simple reaction. The problem is the nitromethane is soluble in the aqueous phase very significantly. So you end up with this situation here. And we think you need to enolize the nitromethane first. So you have to activate it at the interface, and then it will attack. Just to show you that it is an on-water reaction. If you tried under any other conditions, no reaction. Unless you got a base or catalyst or an acid catalyst, no reaction. Throw it into water, 3 hours, pretty much quantitative conversions. What we've done is we study the rate of the reactions under various conditions. Now, I quite like this 3D plot. The problem is it takes a long time to talk through it. So bear with me. Now, we know that the interface area is important, so that depends on stirring rate. So we got the stirring rate as one variable, which is the size of dots. So that those 2 points here, one point is 300 RPM, the other point is 1400 RPM. We've got the temperatures, so blue is 50, 70 is purple, and then finally 90 is red. What's clear here is that the stirring rate doesn't matter all that much. And that's slightly curious because that's in contradictions with the literatures on on-water reaction where stirring and mixing seems to be important. In our case, not so much. The other things we found that the reaction is zero order in the ketone. So you get zero order kinetics. It's got a kinetic isotope effect to the solvents. If you do it in D2O, you got a reaction rate about 2.4 times less than if you do it in water. And the most curious one is that when you add salts to it, sodium chloride, lithium chloride slow down the reaction. So the black one is a sort of baseline reactions. Sodium chloride, lithium chloride very much give you the same response, slower reactions. And sodium sulfate give you much faster reactions. Sodium phosphate give you extremely fast reactions. Okay. So here are some observations of what's unusual about all this. First of all, zero order to ketone. Curious. 70 degree is required for reasonable reaction rate. So if you go to here, the blue one really doesn't give you much rate. You have to go to the purple or the red one. Proton transfer is clearly the rate determining step with that kinetic isotope effect. Now, salt effect is very curious. And finally, the impact of mixing is low. So how do we explain away all this? And this brings us to the biggest problem we face in the last 2 years, the pandemic. So we were very much firing away at these projects, getting some experimental work done, and then the pandemic hit, and we got about 6 months before we can return to the lab. And the nicest thing that we managed to do is that since we have some experience with computational chemistry, we decided actually now's a good time to try to understand all of this with computational chemistry. So we use DFT to study these reactions. And the mechanism is fairly straightforward. You got the nitromethane that needs to be enolized so that it can be a nucleophile, and that we think is catalyzed by water. The water does a proton transfer. Take a proton from the carbon, which is that one, and it put a proton back on the oxygen at that position, and you end up with the enolized version of the nitromethane. Once that happens, it can go and attack the ketone, and the water now act as a scaffold to hold all the partner together, and then you end up with the product. So that explains the on-water acceleration effect. Does a DFT prove it? So the black line is the energy profile for the on-water conditions. We now got the first step being slightly slower than the second step. Now that explains the zero-order kinetics, because the first step doesn't involve the ketone, only the nitromethane and water. The barrier is 30.7 kilocalories per mole, which is quite high. So that explains why we need to heat it up. And it also explains why mixing and stirring doesn't really speed things up, because the intrinsic rate of the chemical reaction is slow. So once you got to a certain mixing level, mixing it harder, that doesn't make any difference, basically. The reaction is not a fast reaction. If you've got a faster reaction, then mixing will become more important. So that's two things we can explain away. Now, if we replace all the water molecules with ethanol, then we got an increase of about 2.7 kilocalories per mole for the activation energy barrier. Now, the second step is the rate determining step. So that again explains why we didn't see much yield of the reaction in ethanol. This needs to be done in water. Only water will be able to accelerate the reactions. Now, the most curious one is the Soul's effect with the sulfate, because we know phosphate are very well-known hydrogen transfer catalysts. So, phosphate can catalyze the first step perfectly, no problem. But sulfate is weird. And all of our reactions are done at pH 7. So there's not much to talk about pH-wise. So what we did is we calculate the same mechanism again, but this time we use the hydrogen sulfate, the HSO4- as the proton transfer catalyst. And you see a massive reduction in activation energy barrier. We just dropped there 9 kilocalories per mole. Normally that means easily an increase of about thousands to tens of thousands of times in reaction rate. So that explains why it's faster, but the concentration of the HSO4 at pH 7 is 10 to the power minus 5 molar only, because the pK is at that point is 1.92. So you got a tiny amount of the catalyst, and that explains why we didn't see that massive increase in rate. It did increase in rate, but the amount of catalyst we have is so small, actually is only reasonably sped up compared to the phosphate. So I'm really intrigued by these results here, especially with this with the sulfate. Now we know that if we go with the only one hydrogen sulfate, then we get a 21.8 kilocalories per mole barrier for the second step. But if we go with one hydrogen sulfate and one water molecule as a bridge between the two partners, we got no barrier. That is a barrier-less reactions. It just goes straight from the intermediate to the product without any problem. Every time we try to optimize it, it goes straight to the product. So this is really fast, and only the first step is a rate determining step. So the last things that we can explain away is, why is it that chlorides now slow down the reaction rather than speeding up the reaction as in Breslow's case? So the reason why it happened is like this. We measure the solubility of water, of nitromethane in water at 70 degrees, and then we measure it in 1 molar of sodium chloride. We get 17% wet weight and 11% wet weight. So with the sodium chloride being added in, it got much stronger ionic strength. It pushed the nitromethane back into the organic phase. So you got less nitromethane available in the aqueous phase to do the enolizations. And because the first step is a rate determining step, that will slow down the reactions. Now in Breslow's case, his reaction all happened in the organic phase. So it doesn't matter. He increased the ionic strength, he pushed all the organic together, he increased the effective concentration, and the reaction go faster. But in our case, one step needs to happen in the aqueous phase, and suddenly the sodium chloride and lithium chloride effect reverse, because we need enough as nitromethane to be in the aqueous phase for the reaction to go fast. So we can explain pretty much every observation that I've raised to you. This one here actually is quite complex. So that's story for another day. I'm not going to talk about that anymore. What I want to talk about is the people who actually did most of this work. Now, the 3 study I show you probably spread out over 10 years, and these are the people who did all the work, and these are the picture of them in the order, the appearance there. I really have to stress that I have the fortunate to work with a very good group of collaborators who really helped me out with many things over the years, sometimes even with career advice. And this group of students and postdocs are extremely talented, every single one of them, who really contribute to most of the things I show you. And one of the things I'm really glad about in my group is that we actually have a relatively good gender balance. I think in the beginning year, we were very skewed toward having male students, but we're much better at this in the recent year. So before I finish, I want to thank all the synchrotron beamline people who are involved in this, the funders, and all the industrial partners who have really contributed to our work of the year. And I thank you all for your attention.
Thank you very much. Thank you very much, Bao, for that fascinating presentation. I'll check if we have questions in the Q&A box. Of course, feel free to add your questions in here and then I'll read them. We have one question from Sam Bates here. This is with regard, I think it's the second part of your presentation on organocatalysis. Mm-hmm. Yes. He's asking how water stable are your new catalysts? For example, the PTMG. He says he actually uses similar catalysts and end up making ureas and carbamates.
Yes. Okay. So interesting things. It's amazingly stable. You're right. These are pretty tricky compounds. So there's another person who does a lot of these, and his name is Philip Jessos, also in the context of carbon dioxide, and he uses the octyl version rather than butyl versions, and he used that to have a sort of very organic hydrophobic guanidine, and then he put carbon dioxide into it, and it becomes something a lot more hydrophilic. But I think the trick here is that the longer the chain you got on the nitrogens, the more hydrophobic it is, the less it will undergo reaction with water because it will repulse water in general. In our case, at 1 mol%, we don't see significant degradations. Now, if you really think about this reaction, you can see that water is a byproduct. At room temperatures, water does not attack our catalyst. At 60 degrees, I think that might happen.
Okay. Thank you very much for that. I don't know if maybe Sam has another follow-up question on that, but I thought that was clear, yes. So I'm just waiting because we still have time for questions. I'm just waiting to see if we have additional questions. Is there one?
Another one there.
Yes. This one says, you give the mechanism of the hydrogen transfer, where there are two water molecules. Do you observe the formation of the Zandel cation in the transition state?
Right. The simple answer is no. Mainly because we didn't look for it. The optimization part seemed to be pretty straightforward with the ionization step. Now, what we've done is actually we tried out every scenario where you got 1 water molecule, 2 water molecules, 3 water molecules to see whether that have an impact on the pathway. And 1 isn't enough. 2 is about ideal. So you need to force it to the right sort of bond angle to get the proton transfer going. But no, I don't think we saw any evidence of that cation in the transition state. We probably will need to look at that again. No, that's a good question, actually. We probably need to look at the molecular orbitals and charges in that particular case. You might be right, but I'll have a look.
Okay. By the way, that was from a question from Konstantinos, if I'm pronouncing that correctly. I think we have time for just one additional question and then we can move on. Maybe a quick one on still on the organocatalysis. Mm-hmm. I'm just keen because the catalysts have such high turnover numbers and turnover frequencies. Are they actually reusable? I'm just going back to the question of the immobilization of the catalyst? Were these immobilized or?
Okay, so the short answer is we don't know, mainly because Rachel, who was brilliant in this project, finished and she moved on. From my experience with other people trying to immobilize guanidine, the bicyclic guanidine are not stable. They hydrolyze really easily. These guanidine are a lot more stable at room temperatures. I don't think I ever seen them falling apart on us, which is the reason why we can push it to 0.1 molar, 0.1 more percent. The reason why you got very funny kinetic curve there is because when you go to that level, you start worrying about impurity and so on, that will start interfering with your reactions, which is not a sort of thing you tend to deal with in bulk chemicals, because actually in bulk chemicals, your starting material tend to be very pure compared to fine chemicals. I have suspicion that this is a lot more stable than the bicyclic version if you immobilize it. And I've seen plenty of immobilized bicyclic guanidine. How exactly stable, how much more stable, I don't know. We never get around to actually doing it. Immobilization is a non-trivial business because you change the kinetic of your reaction completely. You start introducing mass transfer. If with longer chain length, you got all kind of problems with oxidation process as well. So it's not trivial, but I would think it's certainly far more stable than the bicyclic version.
Okay. Thank you very much. Thank you very much. I think in the interest of time, I think we'll move on to